Welcome, Gen Chem Nation. Today in this module we are beginning to talk about acids and bases. And so, to begin, we need to have some general definitions for what an acid is, what a base is, and unfortunately there's actually more than one set. We have the Arrhenius definition. Arrhenius said that an acid is a substance that produces protons and a base is a substance molecule that makes hydroxide. So that's Arrhenius definition. It's really kind of the simplest definition as far as an acid produces protons and a base producing hydroxide. So we could look at some of our common acids that we might be aware of, like hydrochloric acid. Right, this is a source of protons. Or, for the base side of things, sodium hydroxide. So, it's that production of those specific entities. So for our acid, again, there is our proton source. And then for our base, there's our hydroxide. So that's an example of simple acid, Arrhenius acid, and a simple base, Arrhenius base. Hydrochloric acid and sodium hydroxide. It's a little bit of a simplistic definition, though. The next is the Bronsted Lowry definition. And the Bronsted Lowry definition basically says this, it's as far as an acid is a substance that is a proton donor. A base is a substance that is a proton acceptor. So in this definition, we kind of start to see the opposite chemistry between acids and bases. So we're still looking at that idea of a proton. Now we're really specific, just kind of keeping the language within the realm of protons. But we have acid, a proton donor, and that kind of stems from the Arrhenius definition, right? Because we have HCl and it's producing H+, so it's donating H+ to the solution. But it's different in terms of the base, where we have now, a proton acceptor instead of generating hydroxide or a source of hydroxide. With the Bronsted-Lowry definition, often water is part of the acid-base chemistry. So as an example of an acid, we could go back to our HCl example, but show how it interacts with water, where water accepts a proton and becomes hydronium ion, and then we get chloride as well. So in terms of the chemistry, that H plus was donated to the H2O, and that's what's actually formed that hydronium ion. So water is really, you know, a common starting material in a lot of these reactions, until we get to, you know, maybe titrations or things of that nature. But we see water at play a lot within our Bronsted-Lowry definition. A base For example, ammonia is a base, and it also can react with water to produce ammonium plus then hydroxide. So here the H2O is actually donating a proton and that's being donated to the ammonia. So our nitrogen is accepting the proton, and that's what is making then our ammonium ion. So one of those hydrogens from the H2O is the new hydrogen that I'm trying to represent as far as from the water, right? So it's kind of a different hydrogen than the original three. So we see, H2O here kind of acting as an acid, and if we then maybe go back to the first example, we see also here that the H2O is accepting the proton to become H3O plus. So the proton was donated to the H2O, but the H2O is accepting the proton. So H2O is acting as a base in the top reaction, and then is actually acting as an acid in the other. Right, in that donation to ammonia, it's generating hydroxide, which again now kind of still fits with the Arrhenius definition that we're still getting a source of hydroxide, or getting hydroxide within solution. But it's this idea as far as specific definitions, the proton shuffle. Proton acceptance being the base, proton donation being the acid. The next definition, the last definition, is a Lewis definition. And with Lewis, you know, an acid is a substance that is and I wonder what Lewis would put in terms of, you might remember the Lewis octet rule, structure and things of that nature, and when I think of Lewis I think of electrons, and so that's exactly what this definition is really in terms of, is that, you know, an acid is a substance that is an electron acceptor, a base is an electron donor. So Lewis in terms of the actual electrons moving around. As an example, we could look at ammonia reacting with boron trifluoride. And so what we see here is we have nitrogen, which is very electron rich, and we have the boron, which is very electron poor. With the nitrogen, or the ammonia, the nitrogen is the most electronegative, so it, you know, has most of that electron density on it with that lone pair as well. With the boron trifluoride, well, the fluorines, you know, those are the most electronegative elements out there, right? So they're pulling electron density away from the boron. They're making the boron very electron deficient. And so that's what then details, you know, the chemistry. And you make a bond between the nitrogen and the boron. The boron becomes negatively charged and the nitrogen becomes positively charged. And so what's happening here is, well, the nitrogen and its lone pair are donating electron density to make a bond. And so by that nature, that means the ammonia is our Lewis base, because it's the electron donor, and the boron trifluoride is our Lewis acid. So those are the three different definitions that we have. As far as the class is concerned, you know, we will focus most of our attention on the Bronsted Lowry definition. So that's mostly what we are going to be looking at. Part 2 of this module is now getting into, you know, Bronsted Lowry theory. Talking about acids and bases, identifying them, and also getting into strengths of acids and bases. And so the strength basically of an acid or a base is dependent on basically its ability to alter the dissociation of water. also known as the auto-ionization of water. And so we can see that here. We've already somewhat saw this idea earlier, but if we have water, and let's say we have two of them, then we have basically one acting as an acid, so we're looking at it donating H+, and the other H2O is acting as a base, and it's accepting the H+. And so in that reaction you would then get H3O plus hydroxide. So that is the auto-ionization of water. It's actually showing water's amphoteric character. Amphoteric is a property of a molecule that can act as either an acid or a base. So that's the amphoteric nature of water, is that it can actually do both. And so this is, the result from the proton acceptance. The H2O turns into hydronium ion, and this is the result from the proton donation. So that's the auto-ionization of water, and it's defined by a K, specifically equilibrium constant, namely Kw. So Kw is equal to our hydronium ion concentration times our hydroxide ion concentration, and it has a value of 1 times 10 to the negative 14th at room temperature. Negative 14th, at a specific temperature here, 298. So, the value does change. Equilibrium constants, are also temperature dependent. So there's our Kw, and this is how, basically an acid or a base now really alters that idea of the auto-ionization of water, because now it can increase, the hydronium ion concentration, or it could increase the amount of hydroxide, and that's what's resulting in an acidic or a basic solution. So that's how an acid alters the process. It does so by generating more hydronium ion than hydroxide, and this, results in an acidic solution. So if we have a general acid, and we can show it reacting with H2O in an equilibrium process as well to make hydronium ion, and then we would have a minus as a product. So here we have just a general acid, and it, we see increasing concentration of hydronium ion, resulting in the acidic solution. So that's how an acid alters the process. A base alters the process in a similar manner, but it does so by generating more hydroxide. Than hydronium. And so this results in a basic solution. So we could have, a general base, maybe something that looks like this, or we have a lone pair. And so the base accepts the proton, and then that accepts the proton from the water, so we get then hydroxide as the other product. So here we have our general base, and so we are increasing our hydroxide concentration, and that's resulting in a basic solution. Realize that we can also have things that don't affect pH. We're not going to or get into this idea of acidic or basic solutions. We do have neutral solutions. And so there are many molecules that, when dissolved, produce neutral solutions. And this is, by not changing the hydronium ion or hydroxide anion concentrations. So if we took methanol and combined it with H2O, right, we can still write it as an equilibrium, but all that's going to happen is you're going to have methanol that's now aqueous. So there's no production of more hydroxide or more hydronium ion as a result. So that's how these bases and acids affect the actual concentrations of hydronium and hydroxide, and we'll eventually figure it out. Well, that means that we're talking about now changes in pH of solutions. So, in writing these equilibrium reactions, we really have to have understanding of some language as far as parents and our conjugates. So, with equilibrium in, acid-base chemistry, there is basically an acid and base on both sides of the reaction arrows. So, we need a way to decipher one from another. So, for instance, let's go to our general acid equilibrium, where we have HA and H2O. Draw out the molecule so we get a different perspective on how these are being formed. And so that's going to produce our hydronium ion, where now one of the lone pairs has accepted a proton, and the resultant oxygen has a positive charge on it. And then we get a minus on our product side. So again, here we have our general acid. The HA bond is weak, so the lone pair on the oxygen of water grabs the proton, and as a result of that, the bond electrons go on to our A minus. So that's how we get H plus on our hydronium ion, and then that's how we generate also A minus. So here we have water acting as a base, right? It's accepting the proton. We then have hydronium ion, and A minus. Now, if we think about going the other direction, we now have the hydronium ion acting as an acid, and we would have A minus acting as a base. So you can see we have acid and base on both sides. So generally we use the term hydronium ion, so even though it's acting as an acid, we tend to not call it that, we just call it hydronium. And to be honest, same with water, we tend to just realize that it can act as either an acid or a base, and so we just say, oh, it reacts with water. But our A minus has a term associated with it. This is known as a conjugate base. That means on the other side, our general acid is actually a parent acid. And so we have this relationship between parent acid and conjugate base. In terms of general terms, parent acids tend to not have charge, meaning they're neutral. While on the conjugate side of things, we find that conjugates tend to have charge. Right, they're not neutral. So that's one way to recognize it. And they're tied to one another. You know, part of the molecule is A minus. So, you know, we start with the parent, the uncharged form. Really, that's what, you know, really the chemistry that really likes to happen with the molecule is on that parent side. And then we have the conjugate base on the other. We can do the same type of you know, assignment with a general base equilibrium. And so here we were looking at our base being a B with a lone pair, and here is our water. And so now we have the, you know, kind of opposite angle for our water. Water here now is acting as an acid. So it's donating the proton, and those electrons that were in the bond are going on to the oxygen. Our B is our general base. Alright, so it's using its lone pair to accept a proton, and then so that generates then the base with the proton on. That base now is going to have a positive charge, and we generate OH minus, or hydroxide. So going the backwards directions, hydroxide, you know, is technically acting as the base. Going the other direction, while here we have another species that's now acting as the acid. And so this is our conjugate acid. Right, again, it's derived from that base. So here is our parent base. And so these two, again, are tied to one another just like we had above. So that's the nature of these general acid and base equilibria processes. This is how they're increasing the amount of hydroxide, or they're increasing the amount of H+. And so we can see that in both cases. Here with a general acid equilibrium, right, we're increasing our hydronium ion concentration, while with our general base equilibrium we're doing the same thing, but we're increasing our hydroxide concentration. So that's how these act as an acid or a base. And then on the other side we have then the notion of conjugates. All right, we tend not to use hydroxide or hydronium in terms of that conjugate. Usually with the conjugate scenario, it's with the parent and the conjugate. So we either have a parent acid, we have a conjugate base, we have a parent base, we have a conjugate acid. So as kind of an example of some of these, we could say maybe have a table such as like acid, base, and then we could do conjugate acid and conjugate base. So if we have a reaction with acetic acid, and if it reacts with H2O, then H2O would be acting as the base. It's going to produce hydronium ion, which is resultant from the base, so we could call it the conjugate acid, but I tend to just use the word hydronium ion. And then we have the conjugate base, which is acetate. So we have our acetic acid, right, and that is our parent acid, and then that's generating acetate, which is then the conjugate base of acetic acid. So even in the nomenclature, you can kind of see that. As another example, we could look at H2SO3. This is an acid as well, and so it generates hydronium ion, and then after just loss of one proton, we end up with this hydrogen sulfite. But they're all lined up the same there in terms of that type of relationship of acid to base, and then conjugate acid to conjugate base. Notice that all we're doing really is loss of a proton. The starting material, the parent acid, is just losing a proton to the water. If we look at the flip side of that, such as ammonia, now ammonia acts as a base. It's a nitrogen with a lone pair in the molecule, and so it generates ammonium and then hydroxide. So we started here with ammonia in terms of that parent base, and then we're generating ammonium, which is now the conjugate acid form of ammonia. So there's that kind of tie between the two, just like we have above. So now that we have, kind of an understanding of, the beginning, we're starting to get a notion of some language here with parents and conjugates and how they are defined with acids and bases as, proton donors and proton acceptors. Let's now break into, talking about acids and acid strength. So we have, kind of two sides to it. We have strong acids. Strong acids completely dissociate into water. This occurs because of the conjugate and its stability. So as a result, this is really just a one-way ticket to donating protons into solution. So the more stable the conjugate is, the stronger the acid. So, some examples would be like hydrochloric acid, hydrobromic acid, these binary acids, hydroiodic. We also have oxyacids, such as, nitric acid, sulfuric acid, perchloric acid has very strong acids as well. And so with our general acid formula, or form here, really what we're seeing is a one-way process where we have complete dissociation. So basically that means that if you know the concentration of HA, that's equal to the concentration of H2O or H3O plus, right? Because of that idea of 100% dissociation. When we get to weak acids, these only partially dissociate when dissolved in water. Again, the extent of dissociation depends on the conjugate. And now we could actually call it the conjugate acid because we actually do have a backwards direction. So it's that stability idea that really helps the process along with weak acids, as well as with strong. And now we could call it, the conjugate base, because instead of the conjugate, since there is an actual backwards direction, so again, strength is dependent on the stability. In terms of strong acids, we have a conjugate, but it's really not a conjugate base because we only have a one-way direction with our reaction arrow. with weak acids, we have now an equilibrium process. So the more stable the conjugate base, the stronger the parent acid. And so with weak acids, we tend to see a lot of organic acids. And these usually have the CO2H group, where R here is really, kind of anything. The rest of the molecule. And then here we have what's known as a carboxylic acid group. And so that's what usually defines our weak acids, is we usually see this CO2H group. It can be written a couple different ways. So, as I've shown it, RCO2H. Sometimes people write it as RCOOH is one form, or another form would be, actually drawing out the structure, which looks like that. So those are, the structures of the weak acids. We tend to see these being, these types of organic acids, while we tend to see, really strong acids tend to be, inorganic acids. So let's look at then relative acid strength. And let's first focus in on strong acids. Strong acids tend to be inorganic acids. These are molecules lacking carbon. Within strong acids, we have two classes. We have binary acids. And binary acids have the general formula of HX. And so with binary acids, the stronger the acid, the less electronegative X is. So we want to have, basically groups that are less electronegative, and that actually result in a stronger binary acid. Less electronegative also means, normally here, greater size. So as size of X increases, the acid strength also increases. So we have a couple rules there, right? So the less electronegative X is, the stronger the acid. The size of X increases, acid strength also increases. So in looking at some examples of binary acids, we could look at hydrochloric acid versus hydroiodic acid and ask the question, which is stronger? And so we would say hydroiodic acid is stronger. We say that because iodine is less electronegative than Cl, and also I is bigger than Cl. So that means we have a stronger acid because we have a weaker HI bond compared to the HCl. HCl would actually have a stronger bond. And so that's why it's actually not the stronger acid. The stronger acid is the one that dissociates and puts the proton into water, is the proton donor. So the stronger that bond is, well, then the weaker the acid becomes. I mean, both of these are obviously strong acids. It's just saying that hydroiodic acid is actually stronger. We also have oxyacids. And oxyacids are acids that contain, a lot of oxygen. Strength can be determined by two features. The first of those is number of oxygens. The greater number of oxygens, the stronger the acid. And so this has to do with the idea again of stability. More oxygens on the conjugate side of the molecule actually means more resonance structures and greater stability as a result. So that's part A of the breakdown. If you have, the same number of oxygens, the stronger acid will have the central element with greater electronegativity. So the more electronegative the central element, that equals the stronger the actual acid. So if we look at some examples of these, we could look at, for instance, sulfurous acid versus sulfuric acid versus nitric acid. And so here we would say, again, asking the question of, strongest acid. The strongest acid would be the sulfuric acid. It has the greatest number of oxygens. We could do another example and look at H2SO3 versus H3PO3 versus nitric acid, and ask the same question of what is the strongest acid. And so here we have, all have the same number of oxygens, but nitrogen is the most electronegative. So that's why nitric acid would be the strongest of the oxy acids. And that's looking at relative strength of strong acids. One exception that we find within the strong acids so one exception of an inorganic acid that is actually a weak acid, and there are others, but I just want us to know this one is basically hydrofluoric acid. So that's one exception I want us to keep in mind. The HF bond is actually is pretty strong, so it's actually not a one-way process. It's not 100% dissociation. It is an equilibrium process. So now let's look at weak acids. Weak acids tend to be organic acids. And these are ones that, that are containing carbon and are defined by equilibria. So we don't have complete dissociation, right? The groups adjacent to the CO2H group affect the acidity by either withdrawing electron density or by donating electron density. So electron withdrawing groups adjacent to the CO2H increase acidity, while then electron donating groups decrease that acidity. So that's what we have to look at, this idea of electron withdrawing groups that increase acidity, while then we have, electron donating groups that decrease that acidity. And so this, this type of push, and pull on electrons is known as the inductive effect. So if we look at an example, if we just, start, looking at a chain of molecules here where all I'm doing is changing the amount of chlorine on each molecule as we go, we find that our acidity increases from right to left. Right, this Cl is the electron withdrawer. And so we can see we're going from 3 to 2 to 1 to 0. Carbon and hydrogens are actually electron donors. So that's why we see the increase the way we do. We would also see it, in terms of distance. So here, looking at a molecule that has a little bit of a longer chain to it, and what we can do with these is kind of get a sense of proximity. What we're going to find in this example is that they all have the same number of electron withdrawing groups, but they are not all the same in terms of how close they are to the CO2H. So we still see increasing acidity from right to left, and we're seeing the chlorine being right adjacent. If we break these carbon units, down, we can get a sense of proximity of the chlorines or of the electron withdrawers to the actual CO2H. And so the closer they are, the more of an effect they actually have. And so we're seeing the chlorine go from directly adjacent to then 1 away to then 2 away. So that's that idea of the, of electron withdrawing groups and how they can pull away electron density. Maybe get a picture of it. We have, maybe two molecules, such as trichloroacetic acid and just acetic acid. And so if we look, the structures are very much the same, but we have these three chlorine atoms, which are electron withdrawing groups. And so they're basically pulling electron density towards them. And as a result, that is making the OH bond here weak. So we could say that we really have a hydrogen here that's delta plus plus. It really wants to fall off into solution. On the other hand, on the acetic acid molecule, we actually have electron donating groups. So we find that we're actually pushing the electron density the other way. That's now making an actual stronger CO2H bond. And while it still is an acid, we would just say it's, delta plus instead of delta plus plus. So we have, this idea of the inductive effect, right? The electron withdrawing groups make this the stronger acid. Again, the weaker bond as well. While we have a stronger bond on the right, more electron donating groups. And so this is the weaker acid of the two. So that's weak acids, these organic acids, and the inductive effect. One exception I want us to know CF3CO2H, trifluoroacetic acid, is a very strong acid. And it's so strong because of the major electron withdrawing groups it has. So we have two exceptions, HF, which looks like, it's an inorganic acid, but it's actually weak, and then trifluoroacetic acid, which looks like a weak acid, but is actually a very strong acid. So those are just two exceptions I want us to know for the acid side of things. So now let's look at the relative strength of bases. And so we can start with strong bases. Strong bases are basically compounds that completely dissociate into water to produce hydroxide. They are, known as metal hydroxides. So we're looking at like sodium hydroxide, potassium hydroxide, lithium hydroxide, cesium hydroxide, barium hydroxide, right? So we find that we have these metal hydroxides, right? So we have that metal in front is really the tip-off, and then obviously we have OH as well there. And so these completely dissociate due to stability of the metal cation in water. Remember, your ion dipole forces idea with that type of stability. So with sodium hydroxide, if we put it into water, it's kind of redundant in writing it this way. But the hydroxide that we get would accept a proton from water to make H2O, and then that would generate hydroxide, and then you would have your sodium ion. So showing you the chemistry there, but generally we leave out the water since it's somewhat redundant in the process. You can't tell relative strength. Of the metal hydroxides. So there's no real rhyme or reason. We can just say that they're definitely stronger than the second group, right, which is looking at weak bases. And for, again, weak bases, these are molecules that only partially dissociate in water. And again, the strength of the base, depends on the stability of the conjugate acid. The more electron donating groups, next to the nitrogen, the stronger the base. The more electron withdrawing groups the weaker the base. So it's actually the opposite that we find with our acids. We see we really want more electron donating groups to have the stronger base, while withdrawing groups produce a weaker base. Generally, we are looking at amines. These are molecules that contain a nitrogen with a lone pair. So we're looking at this idea of multiple possibilities as we, increase number of hydrogen versus number of, R groups. So these are all amine bases. And we find the same kind of, idea with position and electronegativity, which is the exact opposite. So if we were to look at, for instance, trichloroamine, and we're looking for the strongest base here, where all we're doing is changing how many chlorines are on the molecule. I'm sorry, we should have some NH2s there for this example. And so we find that we have the opposite direction now occurring, that our methylamine is actually the strongest base. And then as we add more and more electron withdrawing groups, we get weaker and weaker. And so that's again because of this idea of electron withdrawing groups or electron donating groups. Here we have, electron donating groups. While the Cl is an electron withdrawing. So you can see as you go from CH3 to, maybe CH2, to then just CH, to then just carbon, right? We see that, we have that, addition of more and more electron withdrawing groups, which makes the base weaker and weaker and weaker. Proximity is also an effect. If we look at, let's say, these two molecules where we have really just one chlorine, but one is a little bit further away than the other. Again, we want to kind of make our map of our carbon units. And so if we ask the question of strongest base, well, that would be then our molecule on the far right. Right, we have more electron donating groups closer to that NH2, while we have more, but they're further away. So we could say, you know, we kind of say it twofold, that our electron donating groups are closer, as well as our electron withdrawing groups are further away. And we can see that pictorially as well, much like we did earlier. By looking at two molecules that just differ with that substitution on the carbon atom. And so here we find, you know, electron withdrawing groups. And what do? Well, just like they did before, is they're going to pull electron density towards them. So that means that my nitrogen, you know, is maybe only a delta minus, right? It still can act as a base, but it just doesn't have as much electron density as what we see on the right, where now we have electron donating groups. And so now we're donating that electron density the other way to the nitrogen. We're really making that lone pair actually bigger, if you will, because there's more electron density there. And so now that nitrogen is now delta minus minus. And so our electron withdrawing groups makes for a weaker base, while our electron donating groups makes then for a stronger base. So that's the inductive effect with both acids and bases. And yes, it can be confusing because it's just, you know, the opposite in terms of, you know, one likes electron donating groups, one likes electron withdrawing groups. And that is looking at, you know, the relative, you know, Bronsted-Lowry theory, getting into what's occurring in terms of, you know, acids generating hydronium ion, bases generating hydroxide in their proton donation and proton acceptance, and then going further into acid and base strength and starting to compare acids to one another as far as which one's stronger, which one's weaker, and then doing the same with that with bases. We'll next get into pH.